Number one, you are looking at what looks like a really big fraction with lots of pieces. But the first thing you should have noticed is that it looks a lot like the difference of squares. So I've got something plus something and something minus something. When I'm going to multiply together, I'm going to get those kinds of things happening. So to get my common denominator, we're going to multiply each fraction by its opposing denominator, right? So we're going to say sine x plus sine y on the bottom there, and sine x plus sine y on the top. And on the other side, we're going to kind of redo that. Cosine x plus cosine y. Now, I'm not really multiplying this out. It is actually foiling all the pieces together, but I recognize that this is the difference of squares. You have the same two things, but one is addition, one is subtraction. And so you can always bank on the idea that that's a pattern involved. It's called the difference of squares. If I square the first part, like this, so it's cosine squared x minus cosine squared y. That's what's going to end up being on if I were to FOIL it all together. The first part squared, the last part squared is going to work. In the middle, I'd get two parts, but they're going to cancel each other out. You're welcome to check that out, do the FOIL process all the way through, but that's the pattern that's going to happen. I'm going to bring that addition sign that's in between the fractions. Then we're going to do the second fraction just the same way. We're going to have sine squared x, not 6, and minus sine squared y. And that's all over those two things put together, right? So sine x plus sine y, cosine x plus cosine y. Now, I have not multiplied that denominator together. Maybe I'm going to need to do that. That would seem like a lot of work. It's not the difference of squares. I would have to take that all the way out. But usually I don't multiply those kinds of things together unless I feel it's necessary, right? Hopefully, when we do things like this, a lot of the time we'll find that things cancel out in the bottom with the top parts. And so I tend to leave them factored apart, right? And at the end, if I need to multiply it together to see what happens, I'll take that step when I feel it's necessary. But I'm not going to do it yet, right? I look at the top part of this, and I think, I see a lot of things together. Do I have the Pythagorean identities, right?
Yeah.
I can look over here, cosine squared x and sine squared x. So I'm going to rearrange this a little bit. We're going to say sine squared x plus cosine squared x. And then it's going to be minus sine squared y minus cosine squared y. All over all of that, right?
Yeah.
What does that top part turn into?
1, 1, 1.
Well, this part is definitely 1. What is this part?
Negative.
They're both opposite signs, right? So it's going to be the opposing sign of whatever sine squared plus cosine squared is. Since that's 1, this turns into negative 1 over all of that. I don't really care what's on the bottom because 1 minus 1 is 0. So that's what our final solution is. 0 over something is always 0. So I'm not going to worry about the bottom because that bottom will not be 0, but it will be some other value. As long as it's not 0, we're good to go. Okay. Number 2. Now, number 1, I think, was a fairly challenging problem, especially to kind of start off with. But once you see it, it should be recognizable. Number 2, on the other hand, I don't think is very difficult. One of our most common tools is to change things into sine and cosine, or some version of sine and cosine, right? That just opens more doors for us, more options that we have. And so I'm going to change that tangent to sine over cosine. I'm going to change the cosecant to 1 over sine on the top. On the bottom, 1 plus tangent squared. I'm not going to change it to sine and cosine, at least not right now, but I am going to change it to secant squared. Keep it one term. I like one term better than I do multiple terms. Right? At that point, I can see that the signs are going to cancel out. That's going to leave me with 1 over cosine on the top over secant. At this point, I can see how I'm going to finish it out. I know the top's going to turn into secant over secant squared. So the top part cancels out, leaving me with 1. Cancels out with 1 on the bottom, leaving me with 1 over secant on the bottom, but that's just cosine. Any questions about that one? All right. And the bottom one, now, I would consider this about as easy as it's going to get, right? From the get-go, you're thinking this is Pythagorean identity, right? So that's cosine squared over sine squared, and that's cotangent squared. If that was really frustrating for you, we need to talk. We needed to have talked a while back, but that one's about as easy as they're going to be. Number 4. Here we have a fraction minus a fraction equal to a single value, a single term. So a lot of times when you have multiple parts equal to one part, you want to kind of get those parts together. So it does kind of lend itself for a common denominator, and getting it together with fractions is a lot like we do with number 1. This one's a little easier. So I'm going to multiply both sides by cosine, or top and bottom by cosine, and this side we're going to do by sine and sine. Here, what is sine times cosecant? 1. Because the reciprocals, right?
Yeah.
Sine and cosecant, or anytime you multiply reciprocals together, you're always going to get a 1. Okay? Minus cosine times cosine, that's going to be cosine squared, over just sine cosine with the same denominator. What do you think's next? Here's our Pythagorean identity. That's sine squared over sine A cosine A. Obviously, one of the signs will cancel out here, leaving me with just sine over cosine, and that becomes tangent. Right? Let's keep moving on. The next one we're going to look at is number 5. I think using the fraction is easier to change, so we're going to start on the right side this time. And so we're going to change that 1 minus cosine squared to, so sine squared x over tangent x. I think changing things to sine and cosine makes sense because what I have on the left side is just sine and cosine. And so we'd end up with sine squared over cosine. Anytime we have a value with a denominator that has a fraction, a lot of the times we always multiply by that reciprocal, so we can hopefully see some things cancel out. So we end up with cosine over sine. When I multiply sine squared times cosine over sine, obviously this sine is going to cancel out with one of those, leaving me with sine x cosine x on the top, which is exactly what I had on the other side. Well, let's move on to 6. 6, depending on your method, 6 can take you a long time or not, right? I'd like to keep it short. Here's one of those times where if I look at what I have at the end, I think I'm going to keep this side. I'm going to work with this side. I've got cosine cubed, and I've got sine squared. I've already got a cosine times something of sine. I've got 2 terms here, so that's not good. But it's kind of already in this format where you're multiplying a cosine times a sine of some value. And so I'm sort of in that term. So what can we do? Yeah, if you look at this term and this term, they have something in common. I really want sine times cosine times cosine times cosine. That would be great if I could get that, because that would be 3 cosines and 2 sines. And let's see what happens. We have sine squared to come out, That's nice, because that's what I really want to have happen at the end. What's left when I factor out the sine squared? You factor out the entire first term, so 1's left over. Minus, you took 2 of those out, so you have 2 left, times cosine. We should recognize the sine, 1 minus sine squared. That's going to be sine squared x times cosine squared x times cosine x. At this point, you're like, yep, that's exactly what I wanted to see. I'm going to rearrange it a little bit so that it looks like the other side. So you're going to have cosine cubed x, because there's cosine squared times cosine, and then sine squared x at the end, which is exactly what we had to start with.